intense techno music means that AP exam is on its way. Yay. All right, gotta make sure I have my own little view of myself and I mute it. I was like, I'm hearing the music a second time. It's because I didn't mute it on my phone, right? All right, well, we're in the middle of rotation. My name's John Frensley, Prosper High School, Prosper, Texas, 30 miles north of Dallas. We got a fresh soaking last night, so it's kind of nice outside. So I'm eager to get out and enjoy the weather. So this particular discussion today is going to mostly be on rotational dynamics, like torque and torque equals I alpha type stuff. I know it says rotational dynamics and energy, but we're really going to hit the energy tomorrow. So let's start with a little warm up here. So I want you to imagine that you've got an astronaut in space. She's just got a bar in front of her. Okay, so we're all at rest, no gravity. Nobody has to think about that. The astronaut has two hands, so she can apply two forces to the bar. So I want you to describe how the astronaut could apply those two forces to the bar in order to accomplish each of these goals. So talk about where on the bar, up, down, left, right, or whatever kind of thing. You can draw a picture if you want. Hopefully you have a piece of paper and maybe a pencil in front of you or whatever, kind of, to play along here. So we're talking about no alpha. B, goal B, yes A, no alpha. C, no A, yes alpha. And then D, yes a both. Okay, so that's the summary of the four goals. There is no acceleration A, no angular acceleration alpha, then one, then the other, then both. All right, so what I'm going to do is I'm going to play a little music here, and you're going to see what you can describe on paper or draw on paper. All right, That's none of that. That's the song that plays in my head anytime I strut confidently down the street. Isn't that great? Okay, you're going to find out the answers a little bit later, so stay tuned. All right, here's our lesson overview. We want you to be able to recite, I mean, that sounds kind of stupid really, but recite all of Newton's laws for translation and for rotation, be able to explain them and apply them, right? Be able to draw an extended body diagram. You won't do that on the actual AP exam because no figure drawing is going to be required, but it might help you articulate an answer. It's a good skill. Or you might be shown an extended body diagram, you have to be able to draw some conclusions from it. So being able to draw, it's a good idea. Then be able to change this extended body diagram into a net force equation and or a net torque equation and solve for something unknown, right? So that's what we're going to work on today. Okay, so here's what you need to know. First of all, you remember how you had Newton's laws of motion, like you already studied, like Newton's first law, if the net force is 0, there's no acceleration, right? Well, there's also 3 Newton's laws for rotation, right? So Newton's first law, if there's no net force, you can't accelerate. Newton's second law, if there is a net force, then there's center mass accelerates. Acceleration center mass is a net force over mass, right? Newton's third law, if A exerts a force on B, B exerts a force back on A, equal opposite direction, happens at the same time, right? Well, now what we're going to do is we're going to do all that, but we're going to pretty much replace the word forces with torques, and we're probably going to change A to alpha, and we'll change mass to rotational inertia, right? But it's the same 3 laws, all right? So here are 3 laws of rotation. So Newton's first law for rotation, if there's no net torque, then the rotation is constant. If there's no net force, then the translation is constant. No net torque, the rotation is constant, right? Example would be the Earth, okay? So the Earth doesn't experience a net torque on its axis. I mean, strictly speaking, there is actually a net torque on the Earth, but I'm not going to get into that today. So the Earth rotates 24 hours a day, right? So the Earth has the same rotation all the time because there's no net torque on the Earth, with the exception I'm going to mention 2 slides from now, right? Okay. Newton's second law, if there was a net torque, then the alpha, the rate at which the rotation changes, would be the net torque divided by the rotational inertia. So just like A equals net force over mass, or net force equals ma, we have net torque equals I alpha, right? So I is rotational inertia, lots of rotational inertia. It's difficult to get it to change its rotational motion very rapidly. And then Newton's third law, well, here's Newton's third law for rotation. For translation, it's if A exerts a force on B, B exerts the same force opposite direction on A at the same time. Well, in the case of rotation, if A exerts a torque on B, then B exerts equal but opposite torque on A at the same time. And just like Newton's third law for translation is secretly the same thing as conservation of linear momentum, Newton's third law for rotation is secretly the same thing as conservation of angular momentum, which we're going to talk about on Friday. So I said a second ago 2 things I contradicted myself. First, I said the Earth has no net torque on it, so the Earth's rotation rate is always the same, always 24 hours. But the truth is that there is actually a little torque on the Earth due to the moon. It turns out it's the same effect that makes the tides on the Earth. And so the Earth is actually slowing down very gradually in its rotation. Like, I think a day is like 1 millisecond longer every week, if you can imagine that, where after 1,000 weeks, a day is 1 second longer. I've heard that somewhere. And so that means that the Earth is losing angular momentum, and it turns out the moon is actually picking it up. So the moon is actually getting just a little bit faster in its orbit, a little bit farther out every day. Isn't that interesting? What a world we live in. Okay, so let's talk about what you had in your warm-up, right? So you got the bar in space. The bar can have exactly 2 forces acting on it. Let's call it a blue force and a red force, just for, just to call them the 2 forces. So is it possible to have no net force and no net torque? Is it possible to have yes net force and no net torque? Is it possible to have no net force and yes net torque? Is it possible to have both? So is it possible to have neither? Is it possible to have one? Is it possible to have the other? Is it possible to have both between net force and net torque? Well, this is exactly what the warm-up was. Okay, so the warm-up said, how can you make it so there's no A and no alpha? Well, no A is the same as no net force. No alpha is the same as no net torque. So this is the same questions, just worded with forces and torques rather than A's and alphas, right? It's the same idea, right? So I say that all 4 of these things are possible. A lot of students think, well, if you have a net torque, you have to have a net force. No, it's possible to have a net torque without a net force. It's possible to have a net force without a net torque. It's possible to have both. It's possible to have neither. So the answer to question 1 is just shown right here. Okay, so how do I have net force equals 0? Well, the two vectors are equal, but in opposite directions, so they cancel the zero net force. And the net torque is zero because both forces act at the same place. So the blue force has produces a counterclockwise torque, and the red force produces an equal clockwise torque because it's the same radius and same force. Torque is radius times force, right? So red points to the right, blue points to the left, equal opposite. Their net force is zero. Red makes clockwise torque, blue produces a counterclockwise torque, same radius, same force, the torques cancel out. So no net force, no net torque. Now I have an animation here where I see a net force, but no net torque. So there's a net force, but no net torque. Both forces are to the right. Right plus right makes a very right net force. But both forces produce opposite torques. The red force is producing clockwise torque. There it is, if I can get on top of my animation there. The red force produces clockwise torque, and the blue force produces counterclockwise torque. So the two torques balance out because the two R times F are the same, but clockwise and counterclockwise cancels out. But the two forces, right and right, add up to a net force. Now, what would it look like if we had no net force, but yes net torque? Here's an animation of that. No net force, because we have a blue left force and a red right force, equal left, equal right, no net force. Notice the net force doesn't care where the forces are applied. Torque cares about where the forces are applied. So if you come up to me and you say, hey, I'm going to apply a left force and an equal right force to an object, all I know is that the object has no net force. But you didn't tell me where on the object you're going to apply the forces, right? So these two forces are applied at two different places so that they produce two clockwise torques. Two clockwise torques, but left and right force balanced to zero force. And then it's possible to have both, it turns out. So here's another example of question 3, where we have two forces that are equal in strength, but opposite in direction. So the net force is 0. And then this time blue produces no torque, but red produces clockwise torque. So it's just another way that you could do question 3. Can you have no net force and yes net torque? And then finally, can you have both? Can you have both net force and net torque? Sure can. I've got a net force because I've got two right forces here, red right, blue right, net force to the right. The center of mass is accelerating to the right. The net force only gets to talk to the center of mass. However, the rotation of the entire object is clockwise, speeding up clockwise, because the red force produces clockwise torque and the blue force produces no torque. So every one of these things is possible. It's possible to have yes A, yes alpha, or yes net force, yes net torque. It's possible to have one or the other. It's possible to have neither. These are all possibilities, and they're all really good conceptual questions that you could be asked. Okay, so now something more tricky. Here's what you're going to do. On your paper, you're going to draw 6 horizontal lines. Horizontal line. They're going to represent the bar in front of the astronaut again. So back to the astronaut in space, we have 6 tasks to do. So bar, 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 bar on your paper. Put a dot in the center for center of mass. Your job is to draw 2 arrows representing forces in order to get these 6 goals accomplished. So just number them 1 through 6. The bar center mass is at rest and the bar does not rotate. Okay, they get more difficult as you get down to 6. Just draw 2 arrows. Don't even label them F, but make a longer arrow for a stronger force, and pay attention to where you apply the forces, where you apply the forces, what direction the forces point, and their relative strengths. All 3 have to be paid attention to. And you only get 2 arrows, not 1, not 3. So you're going to get 4 minutes. That's 40 seconds per part. Spend the least amount of time on part 1 on your mark and set go. I need to strongly advise you a couple of things. One, I'm using PowerPoint, so I get to make my diagrams more fancy than you did. And I put a grid in the background to help me tell where the forces are and how long the arrows are. Two, there's a lot of different answers to each of these. So if yours doesn't match mine, that doesn't mean you're wrong. I'm going to try and describe what needs to be in your diagram in order to be correct, even if it's different from mine. Okay, number one, I'm going to be flipping back and forth between this slide and the next. The center mass remains at rest and the bar does not rotate. Okay, so that's no acceleration, linear acceleration, no alpha. Well, then you just needed to draw two arrows, opposite directions, equal lengths, coming out of the same point. That's all you had to do. All right, so all you had to do was two arrows coming out of the same point, equal lengths, opposite. You have zero acceleration because net force zero, no alpha because there's no net torque. I made mine come out of the center. If you want an upward acceleration but no alpha, you needed two upward forces that were equal and equal distances apart from the center. Yeah, there's a couple other really clever ways to do it, but that's if you did that, you're in pretty good shape. Two arrows coming out of opposite distances from the center of the bar, right? Equal forces. If you want no alpha or no linear acceleration, you needed two forces that were equal in their strength but opposite in direction. To have a clockwise alpha, you needed the torques to produce clockwise the torque, or at least have one produce more clockwise torque than the other one counterclockwise, right? For a downward acceleration and a counterclockwise alpha, I just said I'm going to make both forces down for the downward acceleration. I'm going to make both forces be on the left side so they produce that counterclockwise alpha, right? Now it's hard to see here, but to do an up and right acceleration, I chose an upward force and a rightward force. And notice it's hard to tell, but the rightward force is actually coming out of the center of mass and pointing to the right. I don't know if you can see that arrow, but it's there. So the upright acceleration, up force and right force, and then to get a clockwise alpha, I made the up force produce a clockwise torque, and the right force just doesn't produce any torque at all. And then the last one was really tricky because there was no way to answer it without a diagonal force. The last one said, give me a clockwise alpha, but a rightward acceleration. And so the only way to do that is that you needed to have an up and right force and a down force. Now you could have probably had a down and right force and an up force. So one of the forces had to be up, one of the forces had to be down, and one of the two forces had to have a rightward component to produce the rightward acceleration. Then you had to place them so that they produced that clockwise torque. So again, these are not the only correct answers. These are examples of the possible right answers you could have drawn. Okay, so I hope that was enjoyable. Here's an animation of a wheel rolling down an incline, and then here's the exact same animation but played in reverse, which is basically a wheel rolling up an incline, right? Okay, so everybody take it in. We've got one wheel rolling down the incline, the other wheel rolling up the incline, and there's no slipping, okay? They are not slipping, and that's the whole point of the white dots. The white dots are actually the point where the spokes touch the surface, and so because the spokes touch the surface at each of those white dots, you can know this is not slipping, okay? Now, next time we get together, which is tomorrow, I'm going to show you, and we're going to talk about rolling with slipping, and you'll see that the spokes do not touch the dots. They're not synchronized with the dots. Okay, have we had enough of that? All right, here's your task. I want you to draw two circles on your paper, one for the uphill going wheel and one for the downhill going wheel. I want you to label them uphill wheel, downhill wheel, just two circles. You're going to draw the forces acting on each wheel while it's going uphill or while it's going downhill. Remember, this is an extended body diagram, not a free body diagram. Free body diagram treats the object like it's a little point at the center of mass. Extended body diagram takes into account the shape of the object. Free body diagram does not take into account the shape of the object. Extended body diagram does. So in an extended body diagram, we're going to draw that whole circle, maybe draw a dotted line for the incline to help us for reference. And you're going to draw the forces acting on the wheel, uphill or downhill, and you're going to label the forces, and the arrow is going to emerge out of the point on the wheel where that force is applied. That's an extended body diagram. So here's a couple of minutes to take a stab at it. How are these two diagrams going to be the same? How are they going to be different? On your mark, get set, go. Hopefully I didn't put you to sleep there. All right, so here's what I've done. What I've done is I've taken the wheel that's rolling downhill and I have pulled it off the ramp and blown it up really big for you here on the right so that you can see how it's rotating. Okay, so notice with the animation on the left, I'm watching translation. With the animation on the right, I'm watching its rotation. I have to be able to separate those two motions in my mind. Okay, let's start with the obvious. Everybody say it's like on Wheel of Fortune, RST, ln, and E. In physics, I ask you to draw the forces, mg down, coming out of the center immediately. Okay, so mg down, coming out of the center immediately. You can't see the tip of the arrow because I let it go down too far. It's being cut off by the bottom bar. I'm sorry. Okay. Are you touching a surface? Sure are. So there's got to be some kind of force normal, right? So normal force is going to emerge from the contact point where the wheel touches the surface, and it's going to go perpendicular to the surface, which always goes through the center of the wheel, oddly enough. Yeah, isn't that interesting? The perpendicular to a tangent line has to go through the center. Hopefully we learned that in geometry, right? Okay, well, if this thing isn't slipping, there must be an agent or a force that prevents slipping. Oh, I know who that could be. That's friction, right? So friction opposes slipping. So there must be a friction, and friction always emerges from the same point force normal does because both forces come from the same agent, which is the surface, right? So the friction force points uphill. Now, let's analyze what's going on. Why is it that the wheel is translating down the hill? The wheel's translating down the hill because there's a component of the mg force I call the downhill force, or the mg sine theta force, helping the center mass go down the hill. There's also friction opposing it. So I'm going to say it this way. I drew the components here. Unfortunately, the mg sine theta component got cut off. I apologize for that. I didn't pay attention to that when I made my slides, so shame on me. But what gives the object its translational acceleration A? It has mg sine theta component going down the hill, friction opposing the acceleration up the hill. So mg sine theta minus force friction equals ma. That's a Newton's second law equation for translation. But what about the rotation? Why would the wheel rotate? Can't blame mg. mg doesn't produce any torque. So mg acting at the center produces no torque. Force normal doesn't act at the center, but it points toward or away from the center. Any force that points toward or away from the axis does not produce torque. So mg doesn't produce torque. Force normal doesn't produce torque. The friction force is what produces torque. So the friction is who is to blame for the wheel going faster and faster and faster clockwise. Look at the way the force friction points. It points clockwise around the center. Just take the arrow and follow it around the center. That's how I figure out the direction of the torque produced by a force. I take the arrow of the force, I just follow it around the center. That's a clockwise torque from friction. So force is radius times torque. Torque is radius times force. So the radius is r, the force is force friction, and torque equals I alpha. So that's two equations for Newton's second law for translation. Mg sine theta helps. Force friction hurts. Acceleration mg sine theta minus friction equals ma. But only friction is responsible for torque. So radius times friction, that's a torque, equals I alpha. Okay, so what did you do for the wheel rolling up the incline? Did you draw the weight force? Okay, good. All right. Did you draw the normal force? Oh, good. Okay, very good. Now I know what you're thinking. Of course, there's friction too, right? And if the wheel's going up the hill, then that must mean that that the friction force is opposite the direction the wheel's going, because friction always opposes motion, right? So if the wheel goes uphill, then the friction must point downhill. Well, surprise, nope, the friction points uphill. Wait a minute, the wheel's going uphill and the friction goes uphill? Like the friction's in the same direction as the motion? Yes, friction often is in the same direction as the motion, especially if it's static friction, which is what we have here. We have a static friction here because we're not slipping or sliding. Why would the friction point uphill? Well, the answer to that is look at the way the wheel is rotating. The wheel is rotating counterclockwise, less and less and less counterclockwise. Listen to that. The counterclockwise rotation of the wheel is slowing down. Can't blame mg. It points directly away from the center. Can't blame force normal, points directly toward the center. So how do you slow down counterclockwise rotation? You need a force that points clockwise around the wheel. And in this case, friction, to point clockwise around the wheel, has to point uphill. So a rolling object on an incline, if the rolling object is not slipping, then the friction force points uphill. Whether you're rolling up or down, friction points uphill if an object does not slip on an incline. Isn't that interesting? I hope I've convinced you with this diagram over here why friction has to point uphill. Okay, I want you to look at the red wheel and the blue and the green wheel. They have two obvious differences between them. Both wheels are the same mass and radius, and they have little gray spheres attached to them. Okay, so the wheels themselves have the same mass and radius, but those little gray spheres are in a different place. Right? Okay. You'll notice on the top diagram, the red wheel is taking its time getting down the incline as opposed to the green. The red wheel has less acceleration down the incline. Now, what if we send both of them in the bottom animation toward the same incline with the same translational speed to start with? So they both have the same translational speed to start with, but red goes farther up the hill than green does. There's two ways to explain this. One is an energy way, which we'll talk about tomorrow. And then the other one is talking about torques and forces. That's what I want you to do now. So you're going to explain for the top diagram, why is it that the green wheel has a better acceleration downhill? For the bottom diagram, when they both have the same starting translational speed, why does the red wheel go higher than the green wheel? So why does the green wheel have a greater acceleration down the downhill? Why does the red wheel climb higher up the uphill? All right, that is your task. Right on your mark, get set, couple of minutes. All right, here we go. All right, so let's talk about why does red go slower? Why does it have less acceleration? What did you write? Here's what I say. Both wheels, of the two wheels, red has more rotational inertia. Okay, that's important to say. Now, you might have said, well, it's more difficult to get red rotating, right? Or more difficult to get red to stop. And while I don't disagree with you, I agree with you. I wanted you to explain it in terms of the forces acting, right? Okay, so here's what I'm going to say. Both wheels have the same force helping the center of mass accelerate. They both have the same mg sine theta force helping them go. They both have friction, but the friction on red is more friction. Why? Because friction is producing the torque on red, and red needs more torque for his more rotational inertia. Red needs more torque to get him to rotate. Red is more difficult to rotate. Red needs more torque to help him rotate. Only friction can help out with torque, but more friction, more torque, means more opposing force, making it more difficult for red to translate down the plane. So red has more difficulty translating down the plane because he has more friction opposing his translation, more friction to get him the more torque he needs. Now, the same goes here, actually. So both wheels have the friction pointing uphill this time, right? So remember, both wheels are going to have the same mg sine theta force this time, trying to slow them down. Remember, when you go uphill, the mg sine theta downhill force, what I call it, trying to slow you down. But they both have friction pointing uphill, because on an incline, a non-slipping object always has friction pointing uphill. So the red has more friction, helping it go up the plane. So mg sine theta is trying to slow down both wheels equally, same m, same g, same theta, right? But red has more friction because he has more rotational inertia. He needs more torque to get him to stop rotating. So red has more rotational inertia, so it takes more torque to stop him rotating. So it takes more friction, because that's what provides the torque, but more uphill friction helps the center mass climb the hill before the mg sine theta force has enough time to slow down the red wheel. So in this case, friction helps the red wheel go up the incline more. All right, so there you go. Isn't that glorious? Same backward force, but more forward force, and the red will get farther up the incline before it stops. Okay, so what we're going to do now is we're going to do 4 example problems. I'm going to do 2 of them, and you're going to do 2 of them, right? And all you're going to do is take the situation, draw some forces, write a Newton's second law equation for rotation, Newton's second law equation for translation, then eliminate to solve for the unknown, which is probably just going to be the acceleration of the system, right? Okay, so here's a yo-yo. I have a mass of the yo-yo and a radius of the yo-yo listed here. It really doesn't matter what the numbers are. I just made them up. I have the radius of the inner axis. Remember, a yo-yo has an inner axis that you wind the string around, and it has the outer thing, right? The shell of the yo-yo, right? The rotational inertia is half mr squared. That means I'm treating it like it's a cylinder deal, okay? So here are the steps. The steps are, we're going to make an extended body diagram. We're going to use the diagram to make a net force equals ma equation and a net torque equals I alpha equation. Then we're going to solve for the unknown, which is the acceleration, right? So here's my extended body diagram. It's just tension coming off the inner axis, which is where the string comes off the axis, right? And good old mg down at the center of mass, right? So here's my net force equation. My rule is the direction of acceleration is positive. So since mg helps the acceleration, mg is the positive force. The force that helps acceleration is positive. Force tension is opposed to the acceleration. It counts as a negative force. That means down is positive, and you're going to deal with it. All right. So mg helps. Force tension is opposed to the net force, the acceleration. Right. Now, what am I going to write for a net torque equation? Well, mg doesn't produce a torque because it points directly away from the axis. But force tension does not point toward or away from the axis, so force tension produces a torque. That torque from tension is radius of the inner bit right here. That's that radius right here. I'm pointing with my mouse cursor here. Radius times tension force equals I alpha. So I have my net force equation, my net torque equation. I want to solve for a linear acceleration. So I have my 2 equations here. I'm going to set the table with my 2 equations. Now, I'm going to start by operating on the net torque equation. Look at the net torque equation right here. I'm going to operate on it. So I'm going to plug in the I equals 1/2 mr squared. And alpha is related to linear acceleration through the radius. It's either alpha equals a over r or a equals alpha times r. You need to know your equations that change rotational kinematics to translational kinematics. So I did not take care of my case here because all these r's should be the same r, even though 1 is uppercase and 2 are lowercase. But if you make them all uppercase, or like you're supposed to do, you'll find out they all cancel out. You have left and right cancel, and you have a top and bottom numerator denominator canceling. So, or you can just plug in numbers. That works too. So you get a number you get force tension in terms of A. You get force tension in terms of A. If you didn't plug in numbers, you would have just gotten force tension equals 1/2 ma, right? Now, let's take that force tension and we're going to plug it into the torque, the force equation, right? So here's my mg, here's my force tension, here's my ma. So now all I'm going to do is I'm going to collect together my like terms. I'm going to divide, and I get an acceleration of 1.11 meters per second squared. So you draw the diagram, write 2 equations, net force equals ma, net torque equals I alpha. Then you plug in the I and the alpha to get m's and a's instead. plug the tension back into the net force equation and solve for A. So I'm going to give you 4 minutes to try this on your own with this situation where we have a wheel, and go ahead and use the numbers I've given you, and a hanging block. You get 4 minutes to try this. On your mark, get set, go. Oops. Where's my animation? All right, well, you saw it. It's a wheel with a hanging block. Supposed to be an animation here. It's this. What's the acceleration of that block? Okay, well, that's the end of that. All right, so here's my two, a free body diagram for the block, extended body diagram for the wheel. It's worth knowing that there's always an axis force supporting the wheel, right, that holds it up, has its own mg. I don't care about the axis force and the mg of the wheel because they don't produce any torque. The force tension produces torque for the wheel, and the tension and the mg of the block produce the block's linear acceleration. So I basically explained all that, okay, for the pulley wheel and for the block. If you need to read what I just said, pause the video and read it. Okay, so net force equation. The block has a net force. mg helps it fall. Force tension holds it back from falling. ma is the net force equals ma, right? Net torque equation on the wheel, the tension force is what's producing the net torque. Radius times tension equals I alpha, right? So now I've got my two equations, net force equation for the block, net torque equation for the wheel. And now what I'm going to do, and never say that the block's weight is the thing that produces the torque on the wheel. The block's weight does not act directly on the wheel. Instead, it is the tension force that acts directly on the wheel, not the block's weight. That is a typical mistake students make. It's like, oh yeah, the block's weight is what torques the wheel. No, the tension force does. And the tension force is less than the weight of the block. Okay, so here are my two equations. So let me operate on my torque equation first. So I'm going to plug in A equals alpha R. And you'll notice that I have an R here and an R here, and they don't cancel out. They actually double up. They were supposed to be the same case. I don't know what I was thinking. They should both be uppercase. So then I just plugged in numbers, and I got force tension equals 3 times A when you get all these numbers together, right? So I solve for tension. Then I plugged in the tension in over here in the left side equation, Newton's second law for translation. So I got my mg, my tension is 3 A's, my ma is 2 A's. So add the 3 A's to the 2 A's, then divide, and this block would have accelerated with 4 meters per second squared of acceleration. Okay, two more examples. I'm going to do one, and then you're going to do one. So this is the Atwood machine, and this is the classic Atwood machine where there's no mass or friction at the pulley wheel, right? So this is an ideal pulley, okay? So we have two masses, big M and little m, but the wheel has no mass, no friction. And if that's true, no mass, no friction at the wheel, then the tension is the same on both sides. So how would we figure out the acceleration, right? Well, I'm going to draw the forces acting on the blocks. I'm going to write two Newton's second law equations. I'm going to say the force helping each block go minus the force holding it back equals ma. So for the big block, I have big mg helps the big block go, tension holds it back. Big ma is the net force. For the small block, we have tension helping the small block go up, and mg opposes the small block going up equals ma. So then I take these two equations for the big block. Weight helps it go, tension holds it back. For the little block, tension helps it go, its weight holds it back. Now I'm going to do an elimination. I'm going to add big mg minus force tension plus force tension minus little mg, and the tensions eliminate. I'm going to add big ma and little ma, and they add up. Factor out the the a, and then you can divide. And A is big mg minus little mg over the sum of the two masses. So the net force on the system, big minus little mg, over the total inertia of the system. So I'm going to give you 3 minutes, and then we're going to be done. And so it's net force of the system over the total inertia of the system, right? So now what you're going to do is you're going to say, what if the pulley has mass and its rotational inertia is I, its radius is R? Now, in this case, the tensions are different. You have force tension left, which is not the same as force tension right. So what I want you to do is I want you to set up two Newton's second law for translation equations, green block, red block, and a Newton's second law equation for rotation for the wheel. If you do that, then all the tensions should be able to eliminate when you add all three equations together. So I'm going to give you 3 minutes to try this. On your mark, get set, 3. Then we'll be done. fantasy that I won't go over time, and I always go over time. Okay, well, here we go. Here's the long and the short of it. So the force tension on the left is going to produce counterclockwise torque. The force tension on the right is going to produce clockwise torque, and that's going to result in a net torque equation that that has both tensions in it. Now, the equations we had before for the big and little m's are going to be the same. It's just now the big M is going to be big mg minus tension left. Little m is going to be tension right minus little mg equals MA. So it's not the same tension anymore. It's the same equation, but not the two tensions aren't the same. Now, we're going to take those two equations and we're also going to build a net torque equals I alpha equation. The tension on the left helps produce the counterclockwise torque. The tension on the right produces the opposing clockwise torque. So, and then the pulleys weight and the axis force don't produce any torque. So then I'm going to get this. I'm going to have R times tension on the left helping the counterclockwise motion minus R times tension on the right opposing the counterclockwise motion equals I alpha. So that's a third equation. So here's my rotation equation, and I'm going to plug in A equals alpha over R, or alpha equals A over R. Then what I'm going to do is I'm going to divide both sides by R, and watch what happens. When I divide both sides by R, I get tension left minus tension right equals IA over R squared. Now, notice what I did is I just put the R squared underneath I rather than underneath A. You're allowed to do that. You're allowed to move a denominator underneath a different numerator if the two numerators are multiplying. So I start with torque minus torque equals I alpha. And at the end, I get tension minus tension equals I over R squared times A. So let's put that in with our two equations for the big mass, for the little mass, and for the pulley wheel. Now I'm going to do a big elimination. All six of these things are going to add together. And when all six of these things add together, only the mg's survive because the tension left and the tension right cancel out positive and negative. But look on the right-hand side. I've got my big MA, I've got my little MA, and I've got a new inertia, I over R squared. So it's the same answer as before, but with a new additional amount of inertia. So I factor out the A and I divide. Before, it was the difference in weights over the total mass. Now it's the difference in weights over the two masses and the equivalent mass inertia of the wheel. I over R squared is a number of kilograms. So anytime you're dealing with any situation, the big theme is get the net force on your whole system, get the total inertia of your system, net force over total inertia, and you're good to go. You've got your acceleration. Okay, I'm about done talking right now, okay? If you want to see any of this, you can watch it on the replay or go back. So while I go over the summary, get your print screen buttons ready or your cameras, because there's going to be a big, long list of practice problems. This is encompassing all of rotation that you're about to see, including things that I'm going to talk about tomorrow and that Miss J is going to talk about on Friday. So just be aware of that. So if the forces on object don't balance, then there's a net force, and the acceleration of the center mass is net force divided by mass. If the torques don't balance, then there's a net torque, and the angular acceleration is net torque divided by rotational inertia, right? So same thing with forces and acceleration as with torques and angular acceleration. All right, so this is a long list of questions. I think the bottom one got cut off, but 2009 had two sets of questions. One was called set one and one was called set two, and both sets that are online have a question 3 that deal with something related to rotation. So I put the questions here and I put like kind of which aspects of rotation they go over. Okay, so if you'll go ahead and push print screen, pause the video, or just take a picture with your phone, that'd be great. Okay, and I'm like 10 minutes over time, which is actually probably pretty good for me, but I'm going to invite you to look up my Facebook page and look at my practice problems, Friendly Physics on Facebook, and have a good one.